Hi, I'm Mautika, and this is my project EcoSort. So EcoSort started from a very simple, everyday moment that most of us might have experienced. Imagine you're standing in front of a set of bins that are labeled landfill, recycling, and maybe compost, and you're holding something like a coffee cup or a plastic tray or even a piece of packaging, and you're not fully sure where it goes, and you kind of guess. Individually, that decision feels very small, but when hundreds or thousands of people are making those small guesses every day, those choices add up. It adds up to contamination in recycling streams, to more materials ending up in landfills, and to higher costs for the systems that are trying to manage all of this. So, the core question behind EcoSort is, can images help us understand why sorting is confusing? And can that understanding eventually support clearer and more confident decisions? So for this project, I have three main goals. The first one is to look closely at how common materials actually appear in images. The second one is to build a model that can actually classify those images into six waste categories. And the third one is to use the model's behavior to highlight where the confusion happens and in ways that match what people struggle with in real life. So to begin with, EcoSort is built on the TrashNet dataset. It is a public GitHub repo that's available. And the dataset contains around 2,500 images of everyday waste items that are divided into six categories. They're cardboard, glass, metal, paper, plastic, and mixed trash. And each image shows a single object placed on a very simple background. And even though that the background is controlled, the objects themselves are very natural. They appear in different lighting conditions from different angles and in different states. And this really matters because those small visual differences are exactly what makes sorting confusing in real life as well. And before training the model, the training data set, so the entire data set consisted of 2,527 images, and it had six categories, and it consisted of a mix of JPG and PNG images. And all of them had different image resolutions. And this is the distribution of the data across the six different categories. So some categories have more images compared to the others, like the trash and the cardboard images are lower compared to the other ones. And for cleaning, I just focused on resizing all of them into a consistent resolution so that each sample has the same dimension during training. And any kind of duplicates and corrupted images were removed. And all of them were converted into a consistent RGB format. And the size they were all resized to were 224 by 224 pixels, which is a standard input size for a lot of CNN architectures. So this is an example of before and after. You can see that they're very similar, but the thing that has changed is their resolution, and now they're all consistent. So for training the model, I set aside 80% of the data, 10% for the validation, and 10% for testing. And this is the distribution after cleaning. The distribution shape is similar, but the total number of images is now reduced to 2019 from 2,527. And now they're all in consistent format and they have a consistent folder structure. And at this point, we have six clearly defined material classes, a cleaned, resized RGB dataset, and a train val test split setup for the evaluation. Now, moving on to the methods that I've used. For EcoSort, I focused on CNN. CNN is a really good choice because they're well suited for images. And the main idea behind a CNN is that it scans an image with the small filters and it learns to detect the patterns like the edges, textures, and shapes. And it gradually builds up to more abstract features. So I worked with two related architectures. The first one is a custom CNN baseline, which I called EcoSort CNN, and the second one is a ResNet 18 based model, which uses transfer learning from ImageNet. So the custom EcoSort CNN is a classic CNN design. So this is the architecture, and it takes a 224 by 224 by 3 image as an input, and it passes through four blocks, and then it flattens the result and passes it into a dense layer with about 512 units, and finally a six class output layer. And this baseline is useful because it shows how far a straightforward CNN can actually go when trained from scratch on just this data set. And the second model is ResNet 18. Resonant 18 is a deeper CNN that introduces residual connections, so essentially shortcut connections that allow the network to pass information more easily. And this helps with training stability, and it makes it easier to train deeper networks without losing any kind of important information along the way. So, particularly in this case, I used ResNet through transfer learning. So, I started with a pre trained ResNet 18 that was originally trained on the ImageNet, and then I replaced the final classification layer with a new six class output layer. And then I fine tuned the model on the EcoSort dataset. So, this means that the model does not start from zero. It actually knows useful general features like how to detect edges, textures, and it just needs to adapt those features to distinguish between cardboard, glass, metal, paper, plastic, and trash. And for the training part, these were the key choices made with regard to loss function, optimizer, scheduler, and training length. So I used the cross entropy loss function, and I trained it for up to 20 epochs. And throughout the training, I tracked the training loss and accuracy, and also the validation loss and accuracy. And the training log shows a very steady improvement. Validation accuracy starts from around 80% in the early epochs, and it gradually climbs into the high 80s, and eventually it reaches a really good score of a 94.8% by the last epoch. And this is a strong indication that the model is learning useful patterns without actually overfitting or memorizing the answers. And moving on to the results, once the training was complete, I just evaluated the final model on the held out test set. And the test set are the images that were never used during the training or validation. And on this test split, EcoSort achieved an overall 96% of accuracy. And just looking at the single accuracy number can be misleading. So I also computed a confusion matrix and a classification report with precision, recall, and F1 scores for each of these six classes. So in the confusion matrix, you can see that the rows basically represent the true labels and the columns represent the predicted labels. And the diagonal cells are the ones that the model is predicting correctly. So most of them. And off diagonal cells are the misclassifications. So for echo sort, most of the mass is on the diagonal. That means that the model is correctly identifying the majority of the images in each of these categories. Classes like paper, cardboard, and plastic show strong diagonal values and very few off diagonal entries. And that is almost consistent with the fact that they have more training examples and also visually distinct features. And it's really interesting to see the off diagonal entries because you can see that some cardboards are predicted as um, paper in this case, and that kind of matches with what happens in real life as well. Some thin cardboard pieces can be misclassified as paper, and some shiny plastic objects can be confused as metal. And occasionally, some really messy items just get slided into the trash category. So these patterns line up closely to how people get confused too. And if you show someone a very thin bleached piece of cardboard, they might also be confused that it is a paper. And if you have a shiny plastic wrapper under really strong lighting, it can look metallic. So the classification report kind of backs this up numerically. So you can see that the per class precision and the recall are high across all six materials, including the smaller trash class. And the macro average scores and the weighted average are both around the mid 90s, which suggests that there's a balanced performance and it's not just doing well on the majority classes. So, in summary, the model performs strongly overall. and it does especially well on clear, distinctive materials. It kind of struggles on borderline, visually ambiguous items, which is exactly where humans also tend to hesitate. And I also wanted to see how the model is actually looking at the images, and I use Grad-CAM visualizations to understand that exactly. And Grad-CAM generates a heat map overlay on the original image, and it shows the regions that contributed most to the model's predictions. So warmer colors means stronger influence. And across all of these examples, you can see that it's really focusing on the area where it's kind of getting the idea that okay, this is cardboard. So these visualizations are important because they kind of show that EcoSort is not guessing, and it's actually focusing on reasonable parts of the image. And it also tells where we can improve the model. So for example, if the model is frequently distracted by background clutter, the future data sets could include more examples that kind of teach the model to ignore that noise. So, stepping back, EcoSort answers the original question in a few ways. So, first, yes, images can absolutely help us understand where sorting confusion comes from. So, by training a model and then examining both its successes and its mistakes, we get a structured view of which materials are clear, which pairs are often mistaken for each other, and how differences in textures, thickness, and shine affect perception. So, second, it also shows that high accuracy alone is not the full story. So, the most interesting insights came from the confusion matrix, the per class metrics, and also the Grad-CAM heat maps. So, all of these highlight borderline cases that resemble real life hesitation. So, in terms of future work, expanding the data set to include compostable items and mixed material packaging is something that I can do. And we can also add images that are taken directly from real bins in campuses or public spaces. And I can also build a simple interface or tool that tells where like someone can just take a picture and it can guide them. So on a more personal note, I really enjoyed, working on this project because it kind of helps improving the sustainability goals at a much more local and personal level. And yeah, if you'd like to explore the project more visually, check out the GitHub repo. And thank you for watching.